So welcome to this video on online planning in the continuous action space. So in the last video we actually introduced the concept of online planning or decision time planning, where we actually have the agent at deployment time evaluate certain action sequences and to plan over a certain horizon to actually take actions that give a high return. And while we in the last section focused on discrete action spaces and introduced Monte Carlo tree search as a powerful search algorithm, we in this lecture will focus on the continuous action space. So in order to start off, let's start with an everyday situation that most of you might have already encountered. So just imagine that you see this nice little guy. And the question is now, if you see this guy, give me or come up with a good plan of actions to actually yield the highest reward or the highest return out of the situation. So there might be different action sequences. So you might either take a sequence that actually lets you run away, or you say, okay, I mean the highest chances of surviving this one is just to fight. So what in the end you want to actually do is you want to minimize the probability of getting killed by Jason, given some action sequences AT, and you want to actually minimize this. So you want to find an action sequence A1 to AT that actually minimizes your log probability of being killed by Jason. In other words, in order to frame this a little bit in the model-based reinforcement learning setting, what you actually want to have is you want to maximize the reward you can actually get out of your MDP, or you want to actually find the action sequences that actually maximizes the sum of cumulative reward, such that a certain state as t plus 1 is a function of your forward dynamics model being f of STAT. So this is actually the reinforcement learning perspective on the problem. And in other words, what you actually want to do is, or what you actually want to have is, you want to get your action sequence that actually maximizes your objective function, and you don't care at this point what this objective function is. And what you in the end want to have a set of actions that you're gonna select that maximizes your objective function. So this is actually what you want to actually have, or what you actually want to do. And there's a very simple way of actually doing this in the continuous space. So the simplest method would actually say, pick a set of trajectory sequences of action sequences from some distribution. Might for instance be a uniform distribution, and then just choose the action sequence that actually maximizes your objective function. So you choose the action sequence based on an argmax of your objective function here. Okay, so we actually call this random shooting methods. So how can you actually do this? What is actually the principle behind? What you actually have, you are in some state as 0, and what you actually want to do. So this is maybe something like a goal state. Doesn't matter exactly how this is described. And what you actually do is you just come up with a random guess of an action sequence until some time planning horizon H. So you come up, in this case, with a sequence of 4 actions, just from guess. What you then do is you do an expansion. So actually what you do is you just run your forward model, and you just see that if you execute these actions, you will actually get this states S1 to SH, accordingly to the actions you just took in the states. What you then do is you just evaluate your set of actions that you actually took. So you get an action, you get a trajectory reward, which is just the sum, or this kind of formulas in here. And what you then want to do is, in order to improve everything, you want to do backpropagation. So you actually want to get recursive gradients. And if you remember correctly, so what you actually do is you want to minimize. So this is your objective function that you want to actually minimize. And if you actually roll this thing out, it turns out this thing looks exactly like this. And if this is what you minimize, what you want to minimize, and you want to do a gradient based update on this minimization objective, you can just roll this out and get recursive gradients from it. So this is your objective function, and you derive it with respect to your actions, because this is actually what you want to optimize. And turns out that if you just take the derivatives of all these functions, you see that you can take the derivatives of your reward model, and you see the derivatives of your transition model, and you then actually, if you roll up, so if you remember on this slide, so you do this until you actually reach the full deepness of this trajectory sequence. You actually can compute these derivatives of your states with respect to your actions recursively, and then you can easily apply the chain rule and update your actions and your model accordingly. So this is easily available via some auto-differentiation libraries that are available in modern frameworks such as PyTorch. Okay, so in other words, with the reward model and the transition model derivatives, with respect to the actions, we can update the actions with gradient descent. And if you do this, of course, another step is we can update our actions via gradient ascent and repeat the steps 2 to 5 in order to actually go on with that and actually move this action sequence a little bit towards the goal. So this in principle works. However, it's also is also important to note that in practice it really helps to take second order derivatives. However, we also have seen this in popular policy gradient algorithms such as TRPO, where you also have seen motivations like this. Okay, but it turns out that there is a problem with random shooting methods, and to actually grab a little bit into what's coming now is there is a motivation to actually that motivates actually the concept of colocation. So it turns out, or it doesn't turn out, but what you will see is that so if you just follow the receipt that we have on the previous slide, it turns out that if we change a very early action by a small epsilon, which is a very small change in the beginning, this might lead to a very large change downstream the trajectory. So in other words, as we minimize the following objective, an early action has a very large influence of what's actually happening, although we only change it very slightly. And this means that there will be a large difference in the optimization of such variables. However, but we also know such issues if we talk about the exploding and vanishing gradient problems that we also see in the training of recurrent neural networks. As we actually as we do small changes in here, this might lead us to end up completely at a different position downstream the trajectory. So this is not a very well defined or very well conditioned optimization problem, as we have a high sensitivity in early changes. While we did actually counteract this a little bit in RNN training with introducing of gates and things like this to actually cope a little bit for that, we cannot really change the transition function. This is something we have already seen in the assistance of RL when we actually talked about background planning. So actually this problematic setting means actually that if we only change the action in the very early beginning by only some small epsilon, this leads to large changes downstream, which means that this high sensitivity forms a poorly contingent optimization problem. And it comes up that we can actually introduce the concept of colocation, which actually means that we optimize for states and or actions directly. So this is our original optimization minimization objective. So we want to minimize the so we actually want to maximize in here. So we maximize the reward such that the next state is the output of our forward model. So actually our model that predicts st plus 1 from st and at. And what we actually want to have is we want to collocate the update, meaning that we want to maximize this reward. However, we want that the next state minus the predicted state is actually the same one. So we actually want to have this distance to be equal to 0. This actually forms an explicit optimization constraint, which only leaves pairwise dependencies. So this leads actually potentially to a much larger but an easier to optimize search space. This is a nice graphic that I borrowed from Sergey Levine's class. So while we actually would have made changes in this trajectory in here, we would like really pull the whole trajectory up or down. However, we really try to minimize also the distances between these states along the way, which actually means that we only update over pairwise dependencies in this case. So when we actually compare shooting methods with colocation, we see that when we use colocation, we have a well-conditioned optimization problem. So in other words, changing S1A1 becomes very similar in changing ST80. So there is no large gap in between. It's a larger but easier to optimize search space, and it is very good for context-rich problems. So we have also, you see, there's like two major papers that actually propose using colocation methods. If you're really interested in it, I would really recommend diving into these papers. You will find them in the web. However, in the beginning, actually, we picked the action sequences that we actually want to do when we started random shooting or colocation. We picked an action sequence from some distribution, which could have been also a uniform distribution. Then we run the optimization, and then we choose the sequence of actions that actually maximizes our objective function. And it turns out that the question is, picking an action sequence from a random distribution doesn't really sound like a well thought idea. And the question is, can we do better? And turns out, yes, we can. So we actually can use a very well-known method that is called cross-entropy maximization, CEM. And the conceptual idea of cross-entropy maximization is that we sample our action sequences from some distribution P defined over A. We evaluate all these trajectory sequences, and then we pick the best ones. So we took a number of M, which is usually much smaller than the actual number of samples that we have drawn from the distribution, and then we refit our distribution over A around these best ones that actually achieved very good results. So this is actually the idea behind cross-entropy maximization. So we can also make this a little bit more visual. Cross-entropy maximization is a gradient-free algorithm, which is actually also very nice. It's a population-based thing, like also genetic algorithms, which allows us to escape local optima. And the idea is relatively easy. So we have a starting state in here, and we have a goal state in here. And what we actually do throughout the iterations, we maintain an optimal trajectory, mean, and covariance. So we actually, in this case, so we talk about Gaussians. So we maintain a Gaussian distribution over good trajectory sequences. So we actually do is, in the beginning, we sample Gaussians around the current parameter means. So we sample a lot of actions that actually lead to different trajectories. What we then do is we evaluate, using our model, the sampled parameters, and then we keep actually the best ones. So actually we see that this one is maybe not that well trajectory, and this is also maybe not that well trajectory. And actually what we do is we calculate the returns of all the trajectories and we sort them we sort them in a descending manner. And then we actually refit our Gaussian distribution using the top k samples. So in this case, I mean, the mean changes a little bit, but the variance gets smaller. And in the next step, actually, we only sample around this area, and this lets us actually come to a point where we sample really good trajectories. So cross-entropy maximization is a really easy to implement algorithm. It's like super simple to implement. It's also easy to parallelize because you can actually sample all these trajectory parameters in parallel and evaluate them parallel, and then you just have the fitting in a centralized component. So advantages of CEM in this case: it's super simple to implement. It's also easy to parallelize, so it's like embarrassingly easy to parallelize. But it also has some limitations because actually it seems to fail for high-dimensional action spaces because it's actually really hard. I mean, this is something like you see in many population-based algorithms, so there might be a chance that you actually fail. And as it is a gradient, as you have advantages that it is a gradient-free algorithm, so it can escape local optima, it also has an increased sample complexity, which is something that you would also expect. Okay, there was actually one thing that we also left over as we introduced the shooting and the collocation method. And there I said actually that the usage of first order gradient based optimization is maybe not the best thing that you want to do. And this is also something that we have seen in policy gradients. There's also the idea of using second order information in order to be much more sample efficient and to do much more and faster optimization. And the question is, can we do something like a second order gradient based optimization, such as Newton's method, as we also did it in TRPO? And yeah, it turns out that we can actually do this. So you can actually come up with a linear quadratic regulator called LQR, which is an analytical method that does in second order optimization. And the idea is the following. Actually, you first linearize, so you actually create a locally linear good solutions around your current solution, that you make a linear approximation of it. And then you actually, so you have a linear function of the transition and maybe a quadratic function over the reward, and then you linearly solve or linearly optimize in that region until you iterate over again. So this is actually the same idea as we introduced it very heavily in TRPO, and you can also use it in model-based RL using LQR. So in this sense, they also do it like this. So they have a linear approximation in the transitions and the quadratic approximation of the reward setting. So as it explores gradient information much more heavily, it has a faster convergence. So this is really the case. However, as you have also seen in TRPO, it's a very complicated method that is not easy to understand. And this is also why we will not focus that much more heavily in this lecture in here. Okay, so this already was it for model-based RL in continuous action spaces. I have one more thing to say about auxiliary tasks, which is also something that helps a lot in model-based RL. So auxiliary tasks are things or tasks beside your actual reinforcement learning task. So you have a reward function that defines how good you perform in at a certain task. And what you usually do in order to improve the knowledge of your agent about the world, you introduce auxiliary tasks. Like you can introduce it something like this. So if you're a robot and your task is to do the dishes, you can introduce auxiliary tasks such as washing the tables or cleaning a wall or something like this, which helps you to learn more about your environment. And this knowledge about your environment also helps you to do better in the task at hand. And this is something that you can that you can actually introduce in your agent. And this is also something we heavily discuss in the exploration strategies lecture. So in this case, what I want to spoiler you is actually the idea of curiosity-based exploration. And the idea is actually that you use a forward model prediction error as an intrinsic reward signal to your agent. So what you actually do is you learn a model while training your agent with the usual reward system. You also incentivize your agent to actually learn more about the environment. And how do you do this? You actually you add an intrinsic reward component that you give to the agent, and this intrinsic reward component somehow relates to the mean squared error of what you expect the environment to behave based on your actions. So what you actually do is you simultaneously to the agent train a dynamics model of the environment, and if the agent performs tasks that surprise him or she, and if certain dynamics are surprising, you give the agent a positive reward for doing this. So you actually change dynamically the rewards, the reward setting, which actually incentivizes learning more about the environment. So actually this encourages the agent to revisit states that are novel or unexpected. And this also has ideas that are close to semi-supervised learning, and it also is somehow an idea of building models in the environment and exploiting models in the context of model-based reinforcement learning. But see more about this in the lecture on exploration strategies. So here are some references for the decision time planning for continuous action spaces, and in the next video we will be talking about problems of applying model-based RL in real-world applications. Namely, we will talk about the estimation of and the propagation of uncertainty in our world models.